So now let's proceed. We've looked at Newton's first and second laws that define inertia, mass, and objects in motion, and objects at rest. Let's now move on to Newton's third law of motion. Newton's third law of motion states if two objects interact, the force exerted on object 1 by object 2 is equal in magnitude but opposite in direction to the force exerted on object 2 by object 1. So we're going to see this third law. We're going to use it in a lot of different ways for the next few chapters. It's going to be really fun and interesting when we get into collisions and applying Newton's third law. Forces in nature always exist in pairs. A single isolated force cannot exist. And that's something you need to think about. In nature, the laws of attraction apply here on micro and macro scales. The action force of body 1 acting on body 2 creates a reaction force, body 2, acting on body 1. So you'll notice mathematically when we talk about gravitational force, we've got some gravitational force that we call force prime is equal to the negative of the original force of gravity F. So one of the things that we're going to use a lot then as we start working with Newton's third law is something called the free body diagram. The free body diagram is used extensively in physics and in engineering. And if we look at all of the forces associated on the free body diagram, it allows us to boil down complex parts of a problem or a system and take it apart in pieces and look at individual places. I've got a problem that I've shared with you, a pair of locking pliers. And it shows you how you can take the locking pliers apart in each of its places, each of its pivot points and force points, and determine what the forces are individually and totally of a pair of locking pliers. So in this case, you can see let's start with the force of gravity. We've got the force of gravity, which actually holds this box to the surface. Okay, underneath the surface there, we've got some frictional forces. Sometimes friction is applied, sometimes it's not. We also have an opposite reaction called the normal. And what the normal is, in this case, is just the opposite of the force of gravity. You'll notice that the frictional force is modeled in the free body diagram at the center of mass. You'll notice here that the normal force is modeled on the surface of where the box contacts the surface below. And then we have some force of tension. We could also have some force on the other side here. So this is depicted clearly in an XY axis and allows us to model complicated systems and understand what's going on with them in doing the analysis. Objects in equilibrium and the Newton's first law then say that if I sum the forces and the summation of those forces are 0, that the vector sum of all the forces, the net force acting on an object in equilibrium, there's the key point, in equilibrium is 0. So when you think about this, we've got something that's not moving. It's sitting there happy, dumb, not doing anything, and it's going nowhere. If we look at the component forces associated with sigma F, or the summation of the forces, the summation of all the forces in the x direction will equal 0, and the summation of all of the forces in the y direction will equal 0. And this gives us what's called the first condition of equilibrium. That means essentially nothing is moving. Until you start trying to move the object, then things start changing. And we are no longer in equilibrium, we are now in motion. So in looking at solving a problem like this, we've seen problem-solving strategies before. Let's take a look again. The first thing is make a sketch of the situation described in the problem statement. Try to make it as simple as you can. Draw then a free body diagram for the isolated object under consideration and label all external forces on the object. Then resolve all forces into its x and y components, choosing a convenient coordinate system. Okay, typically, in these types of problems, x and y, Cartesian, rectangular, whatever you want to call it. Then use the equations summing all the x components of force, summing all the y components of force, setting them equal to 0 in equilibrium if nothing is moving. This is called static. Keep track of the signs of the various force components, because one force moving in one direction may be the opposite in the other direction, and it will carry a negative sign. Application of step 4 then leads to the set of equations with several unknowns. Solve the unknowns in terms of known quantities. And we're going to go through this very methodically to determine how do we set up this set of equation and determine where the knowns and the unknowns are. So in this simple example here, a traffic light weighing 100 newtons hangs from a vertical cable tied to 2 other cables that are fastened to the support. So going back to my explanation earlier, 100 newtons here, this includes gravity, mass and gravity. So this is the product of mass and gravity. The upper cables make angles of 37 degrees and 53 degrees. Notice those angles are taken from the horizontal, okay? 37 degrees on one side, 53 degrees on the other. Okay, that's the angle. That's not the outside angles. Those are the internal angles. Okay, so it's made with the horizontal. Find the tension in each of the 3 cables. So if we look at the problem as stated, we've got some tension 1, some tension 2. It makes an angle 53 from the horizontal. This makes an angle 37 from the horizontal. And then we've got T3 that the traffic light is suspended from that knot right there. So if we start taking it apart into its free body components, let's just disconnect the traffic light and say that everything from here up is depicted as tension 3. Everything from here down is the force of gravity. So now if we look at the point where that knot is, where all 3 tensions come together, we have another free body diagram that shows tension 1, tension 2, tension 3. Notice we have tension 3 in the opposite direction along the y-axis, so it carries a negative sign. The T2 tension becomes, in essence, a resultant. T1 becomes a resultant. We have angles associated with them. You should be looking at this now and thinking, well, I'm going to have x and y components associated with each of these tensions. So now what we do is we create from our free body diagram, we create a component solution. Okay, we're going to set up a table. Again, you should be thinking this in terms of maybe I could do this in Excel, and that would be kind of fun. So from the free body diagram, we see that tension 3 is equal to the weight of the traffic light. We're going to neglect the weights of the cables. So we've got tension 1, 2, and 3. We've got each of their components. So now we start to use these component factors of cosine and sine. So we have T1 in the negative direction, cosine, because that's the component on the x-axis. Cosine is 37. T1 on the y component is positive, sine 37. We do the same thing with tension 2. We do the same thing with tension 2 over here, the y component. Notice for T3, there is no x component. There is only a y component, and it's a negative 100 newtons. So the first condition of equilibrium gives us then the equations. 1, summing all the forces in the x direction, T2 cosine 53 minus T1 cosine 37 equals 0. So that's our equilibrium statement. We do the same thing for our y terms, summing all the y terms of force. T1 sine of 37 plus T2 sine of 53 minus the weight of the light, 100 newtons, is equal to 0. So from this, we see that the horizontal components T1 and T2 must be equal to the magnitude. And from 2, we see that the sum of the vertical components of T1 and T2 must balance the force of gravity acting on the light. We can solve then equation 1 for T2 in terms of T1. So we're going to solve one in terms of the other. How do we do that? Well, we have to rewrite the expression. So we're going to grab T2 here, and we're going to say that T1 now is equal to the cosine of 37 divided by the cosine of 53. Okay, so we've rewritten number 1 in terms of T2. And so now when we solve cosine 37, cosine 53, we get 1.33 times T1. Okay, so that's what T2 equals. Now we can take that value and substitute it for T2 in the other equation. So this value, T2, can be substituted into number 2 to give us this relationship. So wherever you see T2, substitute 1.33 times T1. And in doing this, we've got numbers, we've got everything here. The value of T2s are gone. All we have left are T1s. We extract our T1 terms, move them to the other side of the equation, and now we have T1 is equal to 60.1 newtons. T2, now substituting that value into the relationship, gives us 79.9 newtons. Okay, so we've solved one in terms of the other. Okay, so you can see how we used the free body diagram, how we put the components together into a table form, and then solved one equation in terms of the other. Okay, so let's go ahead and stop there.